Hi, this is Sylvia and welcome back. Today I'm going to talk about a new topic and I'm going to talk about the spectrum of spectra. Pretty much the variety of different spectra that we use in earthquake engineering. I'm going to try to gain an understanding of each one. Oftentimes we'll call a response spectrum a design spectrum, and that's okay as long as we don't use them improperly. And so that's kind of what I wanted to go through today, is to highlight all the different kind of spectra that we have. I emptied out my brain, and this is what I found in there. About 17 different kind of spectra. It's cheating because some are subsets of others, but it's pretty much what we have. What I did is I then grouped them in kind of an order that I'd like to go through in this video. We've got three basic kinds of spectra. We got the response spectrum, a scenario spectrum, and a design spectrum. And then within the design spectrum, we have a variety of different kinds of spectra. So I'm going to try to highlight each one of these. What a response spectrum is pretty much the maximum response of an elastic single degree of freedom damped system. And its response really only depends on its natural period of vibration, which is a function of the mass and the stiffness, and its damping ratio. If you have one structure and one ground motion, you have a maximum response. But let's say you've got now a spectrum of structures where the only difference between them is the fundamental period. Let's say they all have the same damping. Typically, you keep damping constant, and then you do it for many different damping ratios. So it's not that you don't account for damping, but you literally just do it for certain damping levels. So you've got your ground motion, you've got your damping ratio, and now you're going to pick a few different structures. And here's an example of 1, 2, 3, and 4 different structures. They have maybe the same mass, but different heights, therefore different stiffnesses, and therefore different periods. Each one is going to have its own deformation response to the same ground motion. And that's because earthquakes have a variety of different frequency content within it, and what we're trying to figure out is what is the response of a damped single degree of freedom systems. It's almost like doing a Fourier analysis, but a Fourier spectrum analysis doesn't account for damping. And damping causes some effects from one period affecting the response in a different periods. So it's not as pure and clean as you would have in a Fourier spectrum response. And so what we do is we look at all these different single degree of freedom system. We look at the maximum response for specified ground motion, and then we can plot this maximum response as a function of period. And that's all that a response spectrum is. A response spectrum is dependent not only on the periods and the damping, but it really depends on the ground motion itself. Each ground motion has its own signature. And the signature, you may see it in the trace of the accelerations, which is what you see here on the right-hand side. Some last for a long time and some don't. And duration can't really be accounted for in an elastic response spectrum. But still, it's something important to take into account. They all have different amplitudes and they have different frequency content. But you may not see certain characteristics in the ground motion trace, and what's important to us is looking at deformable structures, whether it's a geotechnical system or a structural system. And so what we're interested in is the response spectrum, which tells us the signature, but how it's interpreted in terms of a building response. And so what you're going to find out is that this response spectrum, depending on the ground motion, you will have different frequency content. Some have a little frequency content in the short period range, some have more energy in the longer period range. It really depends on the ground motion itself. Oftentimes you'll see it in a linear plot of spectral acceleration versus a period. Oftentimes from seismologists, you see it in a log-log plot. Each one has its own advantages, and I think it's important to learn to read both of them. So that's what a response spectrum is. Maximum response due to a particular ground motion shaking caused by a seismic event. It could be a measured response, but it could actually be a simulated record, okay? It doesn't have to be a real earthquake, but it's an individual earthquake with its own signature characteristics at a particular site or a particular, it doesn't actually matter what your site is. What's really particular is your building. So it doesn't even need to take into account where your site is, because your site is taken into account by the ground motion itself. Okay, so it's whether it's taken at the surface or way down deep, that's what's accounting for the site response. And so that's what a response spectrum is. Then we have a scenario spectrum. Scenario spectrum is a predicted median response. Oftentimes you'll have the median and a standard deviation, but it's very much a predicted response at a single period. So it's not a predicted ground motion. It's telling you the range of ground motion. So if you look here, let's see if these were all for the same magnitude and distance. This will give you plus or minus 1 standard deviation and a predicted median there. So it doesn't give you characteristics of an individual ground motion. It gives you characteristic at each period. And it is a particular site in terms of site class and distance to a particular event, such as an earth, magnitude or a mechanism. And I'll give you a little bit more detail about this, because this is what the ground motion models do, and what we also call ground motion prediction equations. They give you a predicted median response. So they don't predict a ground motion, just a spectrum. And pretty much because that's what they're based on and that's how they're calculated. Then the third type is a design spectrum. A design spectrum is the maximum expected, so it's not predicted, but it's expected demand on a single degree of freedom elastic damp oscillator versus period, so that's the same type of plot, at a particular location with a particular probability of exceedance. And so this doesn't count for a single scenario. Now it's looking at a particular place where you are at your home, let's say, which means that you're different distances and different soil type than you are from somebody who lives across town. They've got different nearby faults, let's say, or maybe they're closer or farther from the San Andreas fault. And so a design spectrum is very much specific to your location. And even within a mile, you may have different soil characteristics. And it has a probability of exceeding a certain something. It could be a spectral acceleration, or it could be a probability of collapse and exceeding a certain probability of collapse. That's what the recent design spectra are based on. But again, this takes into account all possible scenarios. So these are three very different types of spectra. Oftentimes, a design spectrum is often, even the building code calls it a response spectrum. But it's very important, I don't care what it's called, that you understand the different applications and what they physically represent, each one of them. Interestingly, you've all seen scenario spectra. These are the ground motion prediction, the NGA West ground motion prediction equations, the NGA subduction, NGA East ground motion prediction equations, but even BC Hydro and everything else, there's many different ground motion prediction equations all over the world that may be more localized to certain sites. And so you may have seen this scenario in the ground motion portal. When you have to select your ground motion records, you can go through the option of giving a target spectrum being computed by the NGA models. That's a specific scenario. You give it a magnitude, you give it a distance, you give it a soil class and specific values. Here's an example what the input would look like for the NGA subduction spreadsheet, and I'm working on the portal, so you'll see something like what you have for NGA West 2, and there's also an Excel spreadsheet for the NGA West 2 program. And so those are scenarios, individual scenarios that you can compute the estimated response at your site. These are actually used for doing deterministic analysis at your site as well. And I'm going to talk about those afterwards. So we've hit the three general types of spectra, very different uses, very different mechanics behind each one. The design spectrum now brings in a whole bunch of other clauses, as you can see. Pretty much in general, I wanted to show you a really cool figure of a tripartite spectrum, how the spectrum was plotted in the old days, and I still think it's kind of cool. Then we're going to look at the definition of the risk-targeted NCE sub R, which is not the uniform risk spectrum, and I'm going to show you how the risk-targeted MCE sub R is computed either through an idealized map spectrum or through a site-specific spectrum. And here's the uniform risk spectrum right here, it is used to create the NCE sub R. So a design spectrum pretty much is defined by the building code. And so different building codes may define design spectra differently. Since ASC 710, USG, the IBC and ASC 7 is looking at risk target NCE sub R. And so we're looking at the MCE level. And then depending on what you're using, you can be looking at, in ASC 7, you may be looking at the design spectrum being 2/3 of the MCE sub R. Or if you're looking at ASC 41, you're looking at BSE 2 versus BSE 1 versus BSE E or BSE N. So there's many different hazard levels depending on the building code. As I said before, you can determine in two ways, either a mass spectrum or a site-specific spectrum. In the early days, which still holds true, if you plot period on the horizontal axis, pseudo-velocity in the vertical axes, and you plot your response spectrum, you can actually, and I remember I was given a template of this sheet, in this direction is the displacement, in this direction is the pseudo-acceleration, just because they are related amongst them. Well, this spectrum here, this red one, is pretty much what we're used to seeing from our design spectra from the mapped values. But it's really cool to notice, and here it's very easy to see it, is that you've got this constant acceleration range, you've got the constant velocity range, and a constant displacement range. And those are reflected here by the constant acceleration, constant velocity because you got 1/t, and then the constant displacement because you got 1/t squared. And so it's kind of cool how nice things are when you plot log, but you have to plot the pseudo velocity. And so you can actually, depends on which axes. And so the way you would do this is, let's say you've got a structure at a period of point some nice seconds, you go to here. If you go across, you get the pseudo velocity. If you go in this direction, you get the pseudo acceleration. And if you go down here, you get the spectral displacement. So all in one plot, you can get all three quantities. So this is not done this way anymore. But I remember having to do this by hand in the early 90s. The multi-period idealized map spectrum is a new thing that's coming in with ASC 722. So it's got a long way to come down the pipelines. But the web services data is actually there and available, and I played with it. Originally, we started with the 2-period spectrum, which is what we're working with right now. You go to the maps and you input your site lat and long. You returned the S values here. You've got these coefficients as well as the site amplitude, site amplification factors by specifying what your site class is. And the program returns to you the spectral acceleration at these 2 periods. And then you can interpolate all other periods and you get your MCB sub R, which you can convert to your design spectrum. In NEHRP 2020, the process is similar, but it's almost a little bit more efficient. What they've done is, it's kind of cool because they've also added site classes, these intermediate site classes. So there's a little bit more continuous. It's not such a big jump from C to D because you've got a CD boundary type of system. Not only that, but they're also now returning the spectral acceleration at period at 21 periods, as well as the PGA for directly your MCE sub R. It does return all the other coefficients and everything, but you can pretty much pull out the spectrum. So the 2-period spectrum looks like this, and the multi-period spectrum looks like this. And so this is just some random site that I was playing with. You can go to the USGS web. There's a lot of actually graphical user interfaces out there. For me, graphic GUIs are just so 1990s now, where everything is being done through web services, which is awesome because now you can call web services directly from your computation. So if you're in Excel, Excel is really cool because they do have a web services function, but most other programming languages also have it nowadays. And so it's cool because you can just send the information, get it back directly, you can query it, and now you can do many sites at the same time. And it reduces the chances of error. And so now that we've covered, and I think we've kind of covered the risk-targeted NCE sub R for the map spectrum, now we can go on to the site-specific spectrum. Site-specific spectrum gets a little bit more complicated in bookkeeping, and you actually have to have the software for it. There's certain cases for soft sites or even a site class D with high spectral accelerations where the building code makes you do a site-specific analysis. And a nice site-specific analysis is nice because you can do a better model of the hazard at your site as well as your site conditions. So site-specific spectra, as much as, you know, this multi-period spectrum is getting closer to that, it's not quite as personalized as a site-specific spectrum. So the MCE sub R, so the risk-targeted NCE sub R of a site-specific analysis, you can't just look it up anymore. What you've got to do is you do a probabilistic analysis where you get your uniform risk spectrum. The uniform risk spectrum is defined by the uniform hazard spectrum and these mapped risk coefficients that you can get from the USGS. And so the 1% probability of collapse in one method, you can do a more complicated method of integrating in your hazard curves and your fragility functions, but most people just go straight to, you compute your uniform hazard spectrum through your probabilistic seismic hazard analysis. From there, you then look up your site coefficients, you compute your uniform risk spectrum, and you put it right here. And that's the results of your probabilistic analysis. But your MCE sub R is defined as the lesser of the probabilistic or the deterministic. And the deterministic is the 84 percentile response, but it's the envelope. It could be, you know, for every possible scenario, what you do is you do a scenario analysis or you use your ground motion models for each one of your scenarios. So you've got San Andreas fault at such and such a distance, you've got a smaller fault nearby, and you compute the 84 percentile, and then you determine an envelope at all your periods. And so, and you also have a deterministic minimum. Your 84 percentile can't fall below a certain limit, okay? And of course, that depends on your site class. And so now, once you have your, let's say this is your deterministic analysis, and this is your probabilistic, well, if I erase these, your design spectrum is going to be the lesser of the two. And so this is what you call the deterministic cap, and this is what you call the deterministic minimum. And keep in mind that, and I think that comes in the next slide, that once you've done this, you also have to compute your design level earthquake, let's say, which is, according to AC7, is 2/3 of MCE, but it can also not be less than 80% of 2/3 of the mapped value, okay? You can't just say, oh, I did a site-specific analysis and it told me that there's no hazard. So there's always a lower bound to that, to those values. And so you pretty much do is you compute 1, 2, 3, 4, 5, 6, 7 million spectra, you plot them, and then you just take the minimum of the maximum or the maximum of the minimum, and you go from there and you get your design spectrum. It's really not that complicated, but it's really important, therefore, that this is your design spectrum. It's MCE or DE, it's still a design spectrum, and these are all the other components that make up your design spectrum. Your design spectrum does not represent an individual ground motion. If you look in the building code, as I was telling you, there's also some other methods of computing your site-specific spectrum, and here's a nice little graphic that shows you that the risk coefficients are also mapped, and they are site dependent. So we've covered pretty much all the different types of ground motion of spectra that we have. We've got the response, scenario, and design spectra. We've covered them all. Now we get to what's really fun, and I'm just going to highlight what we do when we have ground motions for analysis, and then the concept of the conditional mean spectrum, which then leads to conditional spectra. The building code tells us that I don't care that the MCE sub R is really an envelope of envelopes of estimates. I want you to select ground motions that they're selected that they have the same tectonic regime as those controlling the target spectrum, and shall have a similar spectral shape to the target spectrum. This is what gets me, because I don't think records should have the similar shape to your target spectrum, because you're going to have some ground motions that are shaped like this and they're shaped like this. And so it really should be your average, or your envelope should have the same spectral shape as your target spectrum. But that's in the code, but I mean, similar is enough of a generic term. But then the next step that you have to do is you need to scale the records such that this average, so here's your average of your maximum component, generally matches or exceeds the target response. But you see, they call it response spectrum, but it should actually be the design spectrum. But it's really your target spectrum, because sometimes you need to do something to your design spectrum to. In the old days, you had to take a factor of your design spectrum. So that's why they can't call it the design spectrum. But now your ground motions, the average has to exceed your target spectrum, which is really your design spectrum. And so they are mixing apples and oranges, and that's always a big topic of discussion, because wait a minute, the uniform hazard spectrum or the uniform risk spectrum or the MCE sub R is really an envelope. And so it's really expecting all your ground motions to have all the energy at all periods, which you can see from this nice suite of ground motion isn't the case. And so if you then go to the extreme of spectral matching in a tight form, then now you've got ground motions that all have exactly the same energy content as your target spectrum. And so now this can cause some problems when you've got higher modes that are not excited, or maybe they're overly excited. What is the answer? We don't fully know. But, there's issues between these two concepts as well, because really the design spectrum is meant to be an envelope. Professor Jack Baker from Stanford developed the conditional mean spectrum, where he's saying, wait a minute, if we scale, and this is a big if we scale our ground motions to all have this, a certain spectral acceleration at a certain period, what do I expect the shape of the average of the ground motions to be? And so what he's found is that the shape is closer to something that kind of looks like this. And it's really looking at epsilon values, which is how far are you from your median predictions? How far is your ground motion from the median prediction in terms of sigma? So how many sigmas away from your mean predicted value are you at? So for example, here, this could be a sigma of 2, and maybe this is a sigma of 1.5. Well, the studies that he's done show that he's developed a correlation between the spectral acceleration at one period compared to the spectral acceleration at the conditioning period. But this is all assuming that all ground motions, that the average, so you're scaling all the ground motions to all hit the same point. And so, as much as I didn't hit all the same point, he's saying, well, if they all match here, then the average here and here has a certain shape and a certain correlation. And so he's actually got a closed form solution for that relationship. And so now you can actually, I'm going to jump ahead to this, is you can select your ground motions so that the mean of these ground motions follows a certain relationship. Okay, this correlation that Jack Baker has developed. Not only that, and so that's called the conditional mean spectrum. But you can actually specify and compute what the variability is based on this conditioning point here. Okay, it's very important. And so that's what conditional spectra are, where you're selecting ground motions to meet not just a median, but the median plus or minus 1 standard deviation. And this looks strange because it's plotted in a linear plot. Now, this is saying, hey, these values are lower than maybe my uniform risk spectrum or my MCE sub R. Well, the way that's implemented in the code is if you fall too far below, then you have to pick an additional conditioning period to select ground motions at that conditioning period. So what this turns out to be is that you have at least twice as many ground motions and twice as many analyses that you need to run. Because for this case, where there's 3 periods, it would actually be developed 3 suites of ground motion, and then you process these to look at the envelope and this and this and that. So the conditional mean spectrum may be a little bit more accurate or more physically explainable, but it is a bit more work for the engineering computations. And that pretty much takes us to the end of this video. We've talked about every single type of spectrum. I just really wanted to stay very much high on the surface. Thank you. Bye-bye. I hope you enjoyed this video. Make sure you subscribe and visit my website. Thank you. Bye-bye.